When you say one computer, you mean how large?
You're clever. I mean, one GPU.
I see. I think it's pretty unlikely. I think that there are many. The stack of deep learning is starting to be quite deep. If you look at it, you've got all the way from the ideas, the systems to build the data sets, the distributed programming, the building the actual cluster, the GPU programming, putting it all together. So now the stack is getting really deep, and I think it can be quite hard for a single person to be world class in every single layer of the stack.
What about what like Vladimir Vapnik really insists on is taking MNIST and trying to learn from very few examples. So being able to learn more efficiently. Do you think there'll be breakthroughs in that space that may not need the huge compute?
I think there will be a large number of breakthroughs in general that will not need a huge amount of compute. So maybe I should clarify that. I think that some breakthroughs will require a lot of compute. And I think building systems which actually do things will require a huge amount of compute. That one is pretty obvious. If you want to do X,
right,
and X requires a huge neural net, you got to get a huge neural net. But I think there is lots of room for very important work being done by small groups and individuals.
Can you maybe sort of on the topic of the science of deep learning, talk about one of the recent papers that you released,
Sure.
The deep double descent, where bigger models and more data hurt? I think it's a really interesting paper. Can you describe the main idea? And
yeah, definitely. So what happened is that over the years, some small number of researchers noticed that it is kind of weird that when you make the neural network larger, it works better, and it seems to go in contradiction with statistical ideas. And then some people made an analysis showing that actually you got this double descent bump. And what we've done was to show that double descent occurs for pretty much all practical deep learning systems. And that it will be also, so...
Can you step back? What's the x-axis and the y-axis of a double descent plot?
Okay, great. So you can do things like you can take a neural network and you can start increasing its size slowly while keeping your dataset fixed. So if you increase the size of the neural network slowly, and if you don't do early stopping, that's a pretty important detail, then when the neural network is really small, you make it larger, you get a very rapid increase in performance. Then you continue to make it larger, and at some point performance will get worse. And it gets the worst exactly at the point at which it achieves zero training error, precisely zero training loss. And then as you make it larger, it starts to get better again. And it's kind of counterintuitive because you'd expect deep learning phenomena to be monotonic. And it's hard to be sure what it means, but it also occurs in the case of linear classifiers. And the intuition basically boils down to the following. When you have a large data set and a small model, then small tiny random... So basically, what is overfitting? Overfitting is when your model is somehow very sensitive to the small random unimportant stuff in your data set.
In the training
data set, precisely. So if you have a small model and you have a big data set, and there may be some random thing, some training cases are randomly in the data set and others may not be there. But the small model is kind of insensitive to this randomness because it's the same. There is pretty much no uncertainty about the model when the data set is large.
So at the very basic level, to me, it is the most surprising thing that neural networks don't overfit every time very quickly before ever being able to learn anything. The huge number of parameters.
So there is one way. Okay, so maybe let me try to give the explanation, and maybe that will work. So you got a huge neural network. Let's suppose you have a huge neural network. You have a huge number of parameters, and now let's pretend everything is linear, which is not. Let's just pretend. Then there is this big subspace where your neural network achieves zero error, and SGT is going to find approximately the point. That's right. Yeah. Approximately the point with the smallest norm in that subspace.
Okay.
And that can also be proven to be insensitive to the small randomness in the data when the dimensionality is high. But when the dimensionality of the data is equal to the dimensionality of the model, then there is a one-to-one correspondence between all the data sets and the models. So small changes in the data set actually lead to large changes in the model, and that's why performance gets worse. So this is the best explanation, more or less.
So then it would be good for the model to have more parameters, so to be bigger than the data.
That's right, but only if you don't early stop. If you introduce early stop in your regularization, you can make the double descent bump almost completely disappear.
What is early stop?
Early stopping is when you train your model and you monitor your validation performance. And then if at some point validation performance starts to get worse, you say, okay, let's stop training. If you're good enough.
So the magic happens after that moment. So you don't want to do the early stopping.
Well, if you don't do the early stopping, you get a very pronounced double descent.
Do you have any intuition why this happens?
Double descent?
Yeah.
Or sorry, early stopping?
No, the double descent. So
so I try, let's see. The intuition is basically this, that when the data set has as many degrees of freedom as the model, then there is a one-to-one correspondence between them. And so small changes to the data set lead to noticeable changes in the model. So your model is very sensitive to all the randomness. It is unable to discard it. Whereas it turns out that when you have a lot more data than parameters, or a lot more parameters than data, the resulting solution will be insensitive to small changes in the data set.
Oh, so it's able to, that's nicely put, discard the small changes, the randomness.
Exactly. The spurious correlations which you don't want.
Jeff Hinton suggested we need to throw back propagation. We already kind of talked about this a little bit, but he suggested that we need to throw away back propagation and start over. I mean, of course, some of that is a little bit wit and humor, but what do you think? What could be an alternative method of training neural networks?
Well, the thing that he said precisely is that to the extent that you can't find backpropagation in the brain, it's worth seeing if we can learn something from how the brain learns. But backpropagation is very useful and we should keep using it.
Oh, you're saying that once we discover the mechanism of learning in the brain or any aspects of that mechanism, we should also try to implement that in neural networks?
If it turns out that we can't find backpropagation in the brain.
If we can't find backpropagation in the brain. Well, so I guess your answer to that is backpropagation is pretty damn useful. So why are we complaining?
I mean, I personally am a big fan of backpropagation. I think it's a great algorithm because it solves an extremely fundamental problem, which is finding a neural circuit subject to some constraints. And I don't see that problem going away. So that's why I think it's pretty unlikely that we'll have anything which is going to be dramatically different. It could happen, but I wouldn't bet on it right now.
So let me ask a sort of big picture question. Do you think neural networks can be made to reason?
Why not? Well, if you look, for example, at AlphaGo or AlphaZero, the neural network of AlphaZero plays Go, which we all agree is a game that requires reasoning, better than 99.9% of all humans. Just the neural network, without the search, just the neural network itself. Doesn't that give us an existence proof that neural networks can reason?
To push back and disagree a little bit, we all agree that Go is reasoning. I think I agree. I don't think it's a trivial. So obviously, reasoning like intelligence is a loose gray area term a little bit. Maybe you disagree with that, but yes, I think it has some of the same elements of reasoning. Reasoning is almost like akin to search, right? There's a sequential element of stepwise consideration of possibilities and sort of building on top of those possibilities in a sequential manner until you arrive at some insight. Sort of, yeah, I guess playing Go is kind of like that. And when you have a single neural network doing that without search, that's kind of like that. So there's an existence proof in a particular constrained environment that a process akin to what many people call reasoning exists, but more general kind of reasoning. So off the board.
There is one other existence proof.
Oh boy, which one? Us humans?
Yes.
Okay. All right. So do you think the architecture that will allow neural networks to reason will look similar to the neural network architectures we have today?
I think it will. Well, I don't want to make too overly definitive statements. I think it's definitely possible that the neural networks that will produce the reasoning breakthroughs of the future will be very similar to the architectures that exist today. Maybe a little bit more recurrent, maybe a little bit deeper. But like these neural nets are so insanely powerful. Why wouldn't they be able to learn to reason? Humans can reason, so why can't neural networks?
So do you think the kind of stuff we've seen neural networks do is a kind of just weak reasoning? So it's not a fundamentally different process. Again, this is stuff nobody knows the answer to.
So when it comes to our neural networks, the thing which I would say is that neural networks are capable of reasoning. But if you train a neural network on a task which doesn't require reasoning, it's not going to reason. This is a well-known effect where the neural network will solve the problem that you pose in front of it in the easiest way possible.
Right. That takes us to one of the brilliant sort of ways you've described neural networks, which is you've referred to neural networks as the search for small circuits, and maybe general intelligence as the search for small programs, which I found as a metaphor very compelling. Can you elaborate on that difference?
Yeah. So the thing which I said precisely was that if you can find the shortest program that outputs the data at your disposal, then you will be able to use it to make the best prediction possible.
Mm-hmm.
And that's a theoretical statement which can be proven mathematically. Now, you can also prove mathematically that finding the shortest program which generates some data is not a computable operation. No finite amount of compute can do this. So then, with neural networks are the next best thing that actually works in practice. We are not able to find the shortest program which generates our data, but we are able to find, a small, but now that statement should be amended, even a large circuit which fits our data in some way.
Well, I think what you meant by the small circuit is the smallest needed circuit.
Well, the thing which I would change now, back then I haven't fully internalized the overparameterized results, the things we know about overparameterized neural nets. Now I would phrase it as a large circuit whose weights contain a small amount of information, which I think is what's going on. If you imagine the training process of a neural network as you slowly transmit entropy from the dataset to the parameters, then somehow the amount of information in the weights ends up being not very large, which would explain why they generalize so well.
So that's the large circuit might be one that's helpful for the generalization.
Yeah, something like this.
But do you see it important to be able to try to learn something like programs?
I mean, if we can, definitely. I think the answer is kind of yes. If we can do it, we should do things that we can do it. It's the reason we are pushing on deep learning. The fundamental reason, the root cause, is that we are able to train them. So in other words, training comes first. We've got our pillar, which is the training pillar. And now we are trying to contort our neural networks around the training pillar. We got to stay trainable. This is an invariant we cannot violate. And so
being trainable means starting from scratch, knowing nothing, you can actually pretty quickly converge towards knowing a lot.
Or even slowly. But it means that given the resources at your disposal, you can train the neural net and get it to achieve useful performance.
Yeah, that's a pillar we can't move away from.
That's right. Because if you say, hey, let's find the shortest program, well, we can't do that. So it doesn't matter how useful that would be, we can't do it. So we won't.
So do you think, you kind of mentioned that the neural networks are good at finding small circuits or large circuits. Do you think then the matter of finding small programs is just the data?
No.
So not the size or character, the type of data, sort of giving it programs.
Well, I think the thing is that right now, there are no good precedents of people successfully finding programs really well. And so the way you'd find programs is you'd train a deep neural network to do it, basically,
Right.
which is the right way to go about it.
But there's not good illustrations of that
It
yet.
hasn't been done yet, but in principle, it should be possible.
Can you elaborate a little bit? What's your insight in principle?
Well-
Put another way, you don't see why it's not possible.
Well, it's kind of like it's more a statement of, I think that I think that it's unwise to bet against deep learning, and if it's a cognitive function that humans seem to be able to do, then it doesn't take too long for some deep neural net to pop up that can do it too.
Yeah, I'm there with you. I've stopped betting against neural networks at this point because they continue to surprise us. What about long-term memory? Can neural networks have long-term memory or something like knowledge bases? So being able to aggregate important information over long periods of time that would then serve as useful sort of representations of state that you can make decisions by. So have a long-term context based on what you're making the decision.
So in some sense, the parameters already do that. The parameters are an aggregation of the entirety of the neural net's experience, and so they count as long-term knowledge. And people have trained various neural nets to act as knowledge bases, and people have investigated language models as knowledge bases. So there is work there.
Yeah, but in some sense, do you think in every sense? Do you think there's it's all just a matter of coming up with a better mechanism of forgetting the useless stuff and remembering the useful stuff? Because right now, I mean, there's not been mechanisms that do remember really long-term information.
What do you mean by that precisely?
Precisely, I like the word precisely. So I'm thinking of the kind of compression of information the knowledge bases represent, sort of creating now I apologize for my sort of human-centric thinking about what knowledge is, because neural networks aren't interpretable necessarily with the kind of knowledge they have discovered. But a good example for me is knowledge bases, being able to build up over time something like the knowledge that Wikipedia represents. It's a really compressed, structured knowledge base. Obviously not the actual Wikipedia or the language, but like a semantic web, the dream that semantic web represented. So it's a really nice compressed knowledge base, or something akin to that in the non-interpretable sense as neural networks would have.
Well, the neural networks would be non-interpretable if you look at their weights, but their outputs should be very interpretable.
Okay, so yeah, how do you make very smart neural networks like language models interpretable?
Well, you ask them to generate some text, and the text will generally be interpretable.
Do you find that the epitome of interpretability? Like, can you do better? Like, can you? Because you can't. Okay, I would like to know what does it know and what doesn't it know. I would like the neural network to come up with examples where it's completely dumb and examples where it's completely brilliant. And the only way I know how to do that now is to generate a lot of examples and use my human judgment. But it would be nice if a neural network had some self-awareness about it.
Yeah, 100%. I'm a big believer in self-awareness, and I think that I think neural net self-awareness will allow for things like the capabilities like the ones you described, like for them to know what they know and what they don't know, and for them to know where to invest to increase their skills most optimally. And to your question of interpretability, there are actually two answers to that question. One answer is, we have the neural net, so we can analyze the neurons and we can try to understand what the different neurons and different layers mean. And you can actually do that, and OpenAI has done some work on that. But there is a different answer, which is that I would say that's the human-centric answer, where you say, you look at a human being, you can't read, how do you know what a human being is thinking? You ask them, you say, hey, what do you think about this? What do you think about that? And you get some answers.
The answers you get are sticky in the sense you already have a mental model. You already have mental model of that human being, you already have an understanding of like a big conception of of that human being, how they think, what they know, how they see the world, and then everything you ask, you're adding onto that, and that stickiness seems to be that's one of the really interesting qualities of the human being is that information is sticky. You don't you seem to remember the useful stuff, aggregate it well, and forget most of the information that's not useful. That process, but that's also pretty similar to the process that neural networks do. It's just that neural networks are much crappier at this time. It doesn't seem to be fundamentally that different. But just to stick on reasoning for a little longer, you said, why not? Why can't I reason? What's a good, impressive feat benchmark to you of reasoning that you would be impressed by if neural networks were able to do? Is that something you already have in mind?
Well, I think writing really good code. I think proving really hard theorems, solving open-ended problems with out-of-the-box solutions.
And sort of theorem type mathematical problems.
Yeah, I think those ones are a very natural example as well. You know, if you can prove an unproven theorem, then it's hard to argue you don't reason. And so, by the way, and this comes back to the point about the hard results. You know, if you have machine learning, deep learning as a field is very fortunate because we have the ability to sometimes produce these unambiguous results. And when they happen, the debate changes, the conversation changes. It's we have the ability to produce conversation-changing results.
Conversation. And then, of course, just like you said, people kind of take that for granted and say that wasn't actually a hard problem.
Well, I mean, at some point, we'll probably run out of hard problems.
Yeah, that whole mortality thing is kind of a sticky problem that we haven't quite figured out. Maybe we'll solve that one. I think one of the fascinating things in your entire body of work, but also the work at OpenAI recently, one of the conversation changers has been in the world of language models. Can you briefly kind of try to describe the recent history of using neural networks in the domain of language and text?
Well, there's been lots of history. I think the Elman network was a small, tiny recurrent neural network applied to language back in the 80s. So the history is really, fairly long at least. And the thing that changed the trajectory of neural networks and language is the thing that changed the trajectory of all deep learning, and that's data and compute. So suddenly you move from small language models, which learn a little bit, and with language models in particular, there's a very clear explanation for why they need to be large to be good, because they're trying to predict the next word. Mm-hmm. So when you don't know anything, you'll notice very, very broad strokes, surface level patterns, like sometimes there are characters and there is a space between those characters. You'll notice this pattern. And you'll notice that sometimes there is a comma and then the next character is a capital letter. You'll notice that pattern. Eventually, you may start to notice that there are certain words occur often. You may notice that spellings are a thing. You may notice syntax. And when you get really good at all these, you start to notice the semantics. You start to notice the facts. But for that to happen, the language model needs to be larger.
So let's linger on that, because that's where you and Noam Chomsky disagree. So you think we're actually taking incremental steps, a sort of larger network, larger compute will be able to get to the semantics, be able to understand language without what Noam likes to sort of think of as a fundamental understandings of the structure of language, like imposing your theory of language onto the learning mechanism. So you're saying you can learn from raw data the mechanism that underlies language.
Well, I think it's pretty likely, but I also want to say that I don't really know precisely what Chomsky means when he talks about him. You said something about imposing your structure on language. I'm not 100% sure what he means, but empirically it seems that when you inspect those larger language models, they exhibit signs of understanding the semantics, whereas the smaller language models do not. We've seen that a few years ago when we did work on the sentiment neuron. We trained a smallish LSTM to predict the next character in Amazon reviews. And we noticed that when you increase the size of the LSTM from 500 LSTM cells to 4,000 LSTM cells, then one of the neurons starts to represent the sentiment of the article, of the review. Now, why is that? Sentiment is a pretty semantic attribute. It's not a syntactic attribute.
And for people who might not know, I don't know if that's a standard term, but sentiment is whether it's a positive or a negative review.
That's right. Like, is the person happy with something, or is the person unhappy with something? And so here we had very clear evidence that a small neural net does not capture sentiment, while a large neural net does. And why is that? Well, our theory is that at some point you run out of syntax to model, so you gotta focus on something else.
And with size, you quickly run out of syntax to model, and then you really start to focus on the semantics would be the idea.
That's right. And so I don't want to imply that our models have complete semantic understanding, because that's not true. But they definitely are showing signs of semantic understanding, partial semantic understanding. But the smaller models do not show those signs.
Can you take a step back and say, what is GPT-2, which is one of the big language models that was the conversation changer in the past couple of years?
Yeah, so GPT-2 is a transformer with 1.5 billion parameters that was trained on about 40 billion tokens of text, which were obtained from web pages that were linked to from Reddit articles with more than 3 upvotes.
And what's a transformer?
The transformer is the most important advance in neural network architectures in recent history.
What is attention, maybe, too? Because I think that's an interesting idea, not necessarily sort of technically speaking, but the idea of attention versus maybe what recurrent neural networks represented.
Yeah, so the thing is, the transformer is a combination of multiple ideas simultaneously, of which attention is one.
Do you think attention is the key?
No, it's a key, but it's not the key. The transformer is successful because it is the simultaneous combination of multiple ideas, and if you were to remove either idea, it would be much less successful. So the transformer uses a lot of attention, but attention existed for a few years, so that can't be the main innovation. The transformer is designed in such a way that it runs really fast on the GPU, and that makes a huge amount of difference. This is one thing. The second thing is that the transformer is not recurrent. And that is really important too, because it is more shallow and therefore much easier to optimize. So in other words, it uses attention. It is a really great fit to the GPU, and it is not recurrent, so therefore less deep and easier to optimize. And the combination of those factors make it successful. So now it makes great use of your GPU. It allows you to achieve better results for the same amount of compute. And that's why it's successful.
Were you surprised how well transformers worked and GPT-2 worked? So you worked on language. You've had a lot of great ideas before transformers came about in language. So you got to see the whole set of revolutions before and after. Were you surprised?
Yeah, a little.
A little?
Yeah.
How?
I mean, it's hard to remember because you adapt really quickly. But it definitely was surprising. It definitely was. In fact, I'll retract my statement. It was pretty amazing. It was just amazing to see generate this text of this. And you gotta keep in mind that we've seen all this progress in GANs, in improving the samples produced by GANs were just amazing. Mm-hmm. You have these realistic faces, but text hasn't really moved that much. And suddenly we moved from, whatever GANs were in 2015 to the best, most amazing GANs in one step.
Right.
And that was really stunning. Even though theory predicted, you train a big language model, of course you should get this. But then to see it with your own eyes, it's something else.
And yet we adapt really quickly. And now there's sort of some cognitive scientists write articles saying that GPT-2 models don't truly understand language. So we adapt quickly to how amazing the fact that they're able to model the language so well is. So what do you think is the bar?
For what?
For impressing us that it...
I don't know.
Do you think that bar will continuously be moved?
Definitely. I think when you start to see really dramatic economic impact, I think that's in some sense the next barrier. Because right now, if you think about the work in AI, it's really confusing. It's really hard to know what to make of all these advances. It's kind of like, okay, you got and advance, and now you can do more things, and you got another improvement, and you got another cool demo. At some point, I think people who are outside of AI, they can no longer distinguish this progress anymore.
So we were talking offline about translating Russian to English and how there's a lot of brilliant work in Russian that the rest of the world doesn't know about. That's true for Chinese. That's true for a lot of scientists and just artistic work in general. Do you think translation is the place where we're going to see sort of economic big impact?
I don't know. I think there is a huge number of so first of all, I want to point out that translation already today is huge. I think billions of people interact with big chunks of the internet primarily through translation. So translation is already huge, and it's hugely positive too. I think self-driving is going to be hugely impactful, and that's, it's unknown exactly when it happens, but again, I would not bet against deep learning. So
that's deep learning in general, but you think
deep learning for self-driving.
Yes, deep learning for self-driving. But I was talking about sort of language models.
I see.
Just to check.
I veered off a little bit.
Just to check, you're not seeing a connection between driving and language.
No.
Okay.
Or rather, both use neural nets.
There'll be a poetic connection. I think there might be some, like you said, there might be some kind of unification towards a kind of multitask transformers that can take on both language and vision tasks. That'd be an interesting unification. Now, let's see. What can I ask about GPT-2 more?
It's simple, so not much to ask. It's so you take a transformer, you make it bigger, you give it more data, and suddenly it does all those amazing things.
Yeah, one of the beautiful things is that GPT, the transformers are fundamentally simple to explain, to train. Do you think bigger will continue to show better results in language?
Probably.
Sort of like, what are the next steps with GPT-2, do you think?
I mean, for sure, seeing what larger versions can do is one direction. Also, I mean, there are many questions. There's one question which I'm curious about, and that's the following. So right now, GPT-2, so we feed it all this data from the internet, which means that it needs to memorize all those random facts about everything in the internet. And it would be nice if the model could somehow use its own intelligence to decide what data it wants to accept and what data it wants to reject. Just like people. People don't learn all data indiscriminately. We are super selective about what we learn. And I think this kind of active learning, I think, would be very nice to have.
Yeah, listen, I love active learning. So let me ask, does the selection of data, can you just elaborate that a little bit more? Do you think the selection of data is... Like I have this kind of sense that the optimization of how you select data, so the active learning process, is going to be a place for a lot of breakthroughs, even in the near future, because there hasn't been many breakthroughs there that are public. I feel like there might be private breakthroughs that companies keep to themselves, because it's a fundamental problem that has to be solved if you want to solve self-driving, if you want to solve a particular task. What do you think about the space in general?
Yeah, so I think that for something like active learning, or in fact for any kind of capability like active learning, the thing that it really needs is a problem. It needs a problem that requires it. It's very hard to do research about the capability if you don't have a task, because then what's going to happen is that you will come up with an artificial task, get good results, but not really convince anyone.
Right. Like we're now past the stage where getting result on MNIST, some clever formulation of MNIST will convince people.
That's right. In fact, you could quite easily come up with a simple active learning scheme on MNIST and get a 10x speed up. But then, so what? And I think that with active learning, active learning will naturally arise as problems that require it pop up. That's my take on it.
There's another interesting thing that OpenAI has brought up with GPT-2, which is when you create a powerful artificial intelligence system, and it was unclear what kind of detrimental, once you release GPT-2, what kind of detrimental effect it will have. Because if you have a model that can generate pretty realistic text, you can start to imagine that, it would be used by bots in some some way that we can't even imagine. So like there's this nervousness about what is possible to do. So you did a really kind of brave and I think profound thing, which is started a conversation about this. Like how do we release powerful artificial intelligence models to the public? If we do at all, how do we privately discuss with other, even competitors, about how we manage the use of the systems and so on? So from this whole experience, you released a report on it, but in general, are there any insights that you've gathered from just thinking about this, about how you release models like this?
I mean, I think that my take on this is that the field of AI has been in a state of childhood, and now it's exiting that state and it's entering a state of maturity. What that means is that AI is very successful and also very impactful. And its impact is not only large, but it's also growing. And so, for that reason, it seems wise to start thinking about the impact of our systems before releasing them, maybe a little bit too soon rather than a little bit too late. And with the case of GPT-2, like I mentioned earlier, the results really were stunning. And it seemed plausible. It didn't seem certain. It seemed plausible that something like GPT-2 could easily use to reduce the cost of disinformation. And so there was a question of what's the best way to release it, and a staged release seemed logical. A small model was released, and there was time to see many people use these models in lots of cool ways. There have been lots of really cool applications. There haven't been any negative application that we know of. And so eventually it was released. But also other people replicated similar models.
That's an interesting question, though, that we know of. So, in your view, staged release is at least part of the answer to the question of what do we do once we create a system like this?
It's part of the answer, yes.
Is there any other insights? Like, say you don't want to release the model at all because it's useful to you for whatever the business is.
Well, there are plenty of people don't release models already.
Right, of course. But is there some moral, ethical responsibility when you have a very powerful model to sort of communicate? Like, just as you said, when you had GPT-2, it was unclear how much it could be used for misinformation. It's an open question. And getting an answer to that might require that you talk to other really smart people that are outside of your particular group. Please tell me there's some optimistic pathway for people across the world to collaborate on these kinds of cases. Or is it still really difficult from one company to talk to another company?
So it's definitely possible. It's definitely possible to discuss these kind of models with colleagues elsewhere and to get their take on what to do.
How hard is it, though?
I mean,
do you see that happening?
I think that's a place where it's important to gradually build trust between companies, because ultimately all the AI developers are building technology which is going to be increasingly more powerful. And so it's the way to think about it is that ultimately we're all in it together.
Yeah, it's I tend to believe in the better angels of our nature, but I do hope that that when you build a really powerful AI system in a particular domain, that you also think about the potential negative consequences of It's an interesting and scary possibility that there will be a race for AI development that would push people to close that development and not share ideas with others.
I don't love this. I've been a pure academic for 10 years. I really like sharing ideas, and it's fun. It's exciting.
What do you think it takes let's talk about AGI a little bit. What do you think it takes to build a system of human level intelligence? We talked about reasoning. We talked about long-term memory, but in general, what does it take, do you think?
Well, I can't be sure, but I think that deep learning plus maybe another small idea